Good afternoon, and first I would like to thank the organizing scientific committee to invite me to this and to present an idea. So far it's only an idea for a legacy project on Calar. The project was born in the Max Planck Institute in Heidelberg. It was mainly Neil Deacon, who has left, unfortunately, to England now, who has suggested many parts of it, and specifically he suggested the acronym. So I'm not responsible for this very nice acronym. And from Heidelberg, it's myself as a panic guy, also interested in quasars, Brown Venemans, who is part of the key project in our institute connected with both Pan-stars and the Vista Viking surveys and so on, to find the highest redshift quasars, and he is part of the team that detected the redshift 7 quasar. Bertrand is a guy very much interested in finding the coolest stars, the coolest brown dwarfs, and Remco has made his name for very accurate black hole in the centers of galaxies, black hole measurements. But he's also interested in this kind of survey. And Neil is also working on is working on Pan-stars, and interested in therefore. Short overview of what I want to show. First of all, why should we do it? Secondly, what is panic? In a very short time, some observing experience with panic, and the first ideas about who could participate, and also ideas how to solve the observing and data reduction thing. The final thing is the current status and where to go from here. This view graph should, in basically a minute or two, convince you that it would be a legacy project for the Calar Alto. First of all, I would like to start to tell you why at least one near-infrared band is very important for the science of both the brown dwarfs on one side and the very distant quasars on the other side. Here I have a typical spectra of a T dwarf, a redshift 5.8 quasar, and a redshift 6.5 quasar. You find the quasars easily by looking first for I-band dropouts, and here for the very high redshift quasars, C-band dropouts. But the problem is that if you have only these bands here, the color of a T dwarf and a quasar looks very similar. This changes immediately if you take the J band as a fourth filter, because then the quasar is blue. Even if it's a redshift 6 quasar or above 6 quasar, it's blue, while the T dwarf, or the very cool star, is still very red. If you show that in the diagram, for instance, in the I1 minus Y and C minus J, then you see that the stars follow a main sequence in the sense of colors, and the quasars, because of this very sharp break here, go up here. So if you have a very red object. It could be either a T-dwarf or L-dwarf even, or quasar, but that is depending on the J-band magnitude or J-band brightness. The problem is that for all these kind of things, Pan-STARRS is covering the entire north and going even below the equator. This is a 3 pi survey. You need a near-infrared band, and 2 Mars is not deep enough. What is deep enough is the UKIDS area survey, and therefore a lot of the quasars found in our key program have a combination of Pan-STARRS and UKIDS. But because UKIDS is done with the, or was done with the UKID, and UKID cannot look north of 60 degrees declination, there's a complete empty space up here, and this is the area between 60 and 90 degrees which is missing. And the Calar Alto is perfectly placed to fill this hole. Very short remarks about Panic. Panic is a wide field near-infrared instrument, has 2x2 Hawaii 2 detectors. The pixel size is 18 micron. Capacity is not so important. Readout noise is okay. And we reduce the f8 focal length of the 2.2 to with additional optics developed here in Granada by Conchi to 2.2 meter to f4 at the 2.2 meter telescope. No, I'm back to this one. Sorry, I hit the wrong button. This is the first, an image of the first night, and it shows you the field of view. The moon, unfortunately, was very close by. It was very near perigee. Therefore, it did not fit completely onto this instrument. Also, normally it does. So with the 4 detectors, we have a gaps of protected on the sky 75 arc seconds, and the entire field is 32 with this gap in between, and the pixel scale is on the sky is 0.45 arc second for perfect seeing, and Calar Alto has not seldom perfect seeing, at least that's my experience, at the 2.2 meter telescope. It's not perfectly sampled, but for wide field applications it's good. One important thing to get a continuous sky map or continuous image of the sky is you have to fill these gaps by dithering, and my favorite pattern, which I have used for all observations in the last 2 years, looks like this. This is just the representation of the 4 detectors. So this is the useful area, and if you dither across the gaps, then you can fill the field. You see, if you, this is the first, or the second dither, so to say. You see, there remain 2 areas out there that are not filled after the first dither, and altogether it's a 5-point dithering. That means in these areas here, the optimum what you can get is 3 exposures. So remember, or keep in mind that if you have 5 positions with these gaps, then you have a small area where you have only 60% of the exposure time. That cannot be solved. Oh, sorry. So we are here. So this is the next one, next one, the next one. So it looks completely covered, but in here, if you look very carefully, there are positions where only 3 images have been observed. Okay. The first thing for a wide field survey, a really wide field survey, several thousand square degrees, was to test the optimum observing strategy with this instrument and how fast you could do a large area. What I did was a 5 square degree field. As I showed you in the beginning, the field of view of panic is only a quarter of a square degree. So 5 square degrees means 20 pointings. I cannot show all the 5 square degrees are reasonable on this screen, but what I can do is to show you the two square degrees of that, the first 2 degrees of that. So, why is it doing back almost? Well, because I'm on the wrong side. So that is the first one, first exposure. And the next one, next one, next one, further on, further on. These are data reduced with a quick look of José Miguel. You see even the quick look at the telescope, this was at the telescope. Even that produces pretty nice and filled areas. There are 2 NGC objects on this in this field. This is the open cluster NGC 6939, and there's a galaxy 6986. The 5 square degrees go onto there, but I couldn't present them otherwise you wouldn't see anything. If you look closer, this is a zoom image of the very image, closer to the open cluster, you see the nice image quality. So that is much superior to what you have, for instance, from 2 mass or so. Deeper and superior. Altogether, to do this 5 square degrees, I needed, including all the overheads and so on, all the shifting the telescope, or repositioning the telescope and so on, 160 minutes, I mean, a little more than 2 hours, and at each point at the sky, at each of the full 5 times exposed points, we have 5 minutes. Here's another example that is part of my current scientific work with panic. This is the field of 2 clusters, April 901 and April 902. And the project is to use the bracket gamma filter, which is now available at Panic, bracket gamma filter to observe the partial alpha star formation or the star formation rate in the galaxies of this cluster using the partial alpha line, which is much less affected by dust extinction than H alpha, but has the same properties in a sense. And this is possible because the cluster has the correct or suitable redshift, and so the partial alpha line is right in the middle of the bracket gamma filter. Here, as an example, how good the data are. Here you have still some stripes. It's also this, the pipeline of San Miguel, and here you see that in fact the data. This is one K-band exposure of 10 minutes or so. A mosaic of 10 minutes, and you see that is very, very good image quality. Okay, that was the starting point to test how long you will take with this instrument and this telescope to survey a large area on the sky. I started with 5 square degrees. You will see in a second that this is not good enough. Okay. And again. So I have mentioned that already, that the UKIT's large area survey is using a lot. And the lot is basically this. All this is the 60-degree declination. So the idea of the CANIS project is to observe all this with panning. All this is something like 2,770 square degrees. One pointing is a quarter of a square degree, so this is more than 10,000 pointings. If you reduce this area by taking out the area of the galaxy with less galactic latitude less than 10 degrees, then you can reduce this to 2,400 square degrees. I think this is reasonable for the reason that for the galaxy, a J-band equal limiting magnitude 19.6 or 19.5 survey is not really of much use. So I would think that for the galactic plane, you should have a different survey. By the way, these are the 5 square degrees where I tested the whole thing. And because I have tested this, I know that for getting the full 2,400 square degrees, I need 150 nights with a typical, I assume the typical length of the night of 8.5 hours per night, which is not unreasonable for the Calar Alto in the J-band. If you want to go into pure extragalactic, very distant work, then you could even say the high priority area is the one where the extinction is less than 1/10 of a magnitude, and you will reduce the field even further. But this is the reference number for the Calar Alto Northern Infrared Survey. The possible institutes and collaborators start obviously with the Calar Alto. We will be in it, certainly, as long as we are allowed to use a 2.2 meter telescope, which is at the moment until end of 2018. I have asked Mathilde to provide me with somebody who is interested here in Granada, the IA, in this kind of survey. I have not heard a name yet. If somebody of you stands up and tells me, yes, I want to join, please do so. Okay? In addition, one could bring together a collaboration of more scientists, individual scientists throughout the countries of Germany and Spain, so we could use open time. And my idea also is that for other institutions, and I have in mind 4 instance institutions that did UKITs, they could also buy into the survey by buying time in Alto. Jesus told me this is the actual number for clear and fundamental guaranteed service A night. So my dream would be that half of these 150 nights are bought by institutions. This would support the, for my opinion, underfunded Calar Alto Observatory considerably. Okay. For the reduction of this data, I would think that the panic pipeline, or PAPI, is in a, sorry? is now in a very good shape, and so for the first step, I have no problems to assume that you can do it with the PAPI pipeline, with the system double. It's a PAR pipeline, or the panic pipeline. And so flat field reduced text and mosaic fits in images coming out from the PAPI software can, for my opinion, very easily be produced. This is here a list of images that are put into a kind of a catalog, text ASCII file, and they all will all be reduced in very short time with a normal, not too expensive PC or machine. That is the first step is very easy, and my guess would be at the moment, from my own experience, that you need a person to do this. You need a person day per observing night. But that's not the end for a survey like UKITs, to compare with UKITs or so. So you have to go further. And I just call this pipeline continuous. The next step is to do object detection and classification for the metric and astrometric calibration. And my dream or my idea is to involve the Cambridge Astronomical Survey Unit in this thing, because they have done this for the entire UKIT survey, and they are very capable to do it. So one only has to convince them that this is worth doing, and then put the data further to the Whitefield Astronomical Unit in Edinburgh, that is also storing all the UKITS data and also VISTA surveys, and provides not only the archiving but also the database access and so on. So this is the Whitefield Astronomy Unit. So far, the project is evolved. As you might have realized, I was very loose in mentioning collaborators. I have not really spoken to the people in Edinburgh and in Cambridge. And the reason for that is what I will show now. The current status of panic. The current status of panic is that we have these 4 detectors, and obviously this detector in the southeast quadrant is extremely bad in terms of 20% bad pixels. And that was exactly the reason that after that this 20%, the current number, bad pixels, that this part, this quadrant 4, was missing in the data from my project. The Q4 was open, and this is because the pipeline works with 2 mass stars. And here in this detector, it's even impossible to identify the 2 mass stars. So you cannot do the astrometric alignment at all. So at the moment this part here is useless. And unfortunately also this part up here is deteriorating, and it depends on the position on the sky whether the puppy can work on this detector or not. That means whether it can identify enough 2 mass stars. Near the galactic plane, and that was this 5 square degree area, this was near the galactic plane. Therefore there was no problem even in this detector. But if you go to extragalactic fields, then it does not work. The good news came this August when the Calar Alto got the fund from this European regional fund, and it's an amount of 530,000 euros. That was 80% because of the European fund. There's 80% only. This was 80% of the money needed for buying 2 Hawaii 2 detectors to replace the 2 bad ones. The extremely bad one and the bad one. But unfortunately, I have to tell you that is not the solution yet. And the problem is the following. After the funds, after this was granted, I immediately asked our detector people to contact Teledyne and ask for a price, a recent price for replacing these detectors. And that's the answer. The Hawaii 2 detectors are no longer made with the same packages as the ones you received in 2008. And the new detectors, the new SEA science arrays, are not easy to replace into your mosaic. And that was their offered alternatives. Either you replace all 4, or you replace the 4 detectors by one 4K by 4K detector. This alternatives, because there was first some discussion back and forth between Heidelberg and Teledyne, and I didn't understand everything. This is the only alternatives I know exactly for 1 week now, and therefore I cannot offer you a solution. I have thought about the two possibilities. First of all, Peter Bitzenberger from our institute has had a phone call with Teledyne last Friday night. Fortunately, I haven't seen him since then, but I have email contact. And he has not he didn't get a real answer of what this would cost. But the idea is, if we give, or his idea is that if we give back the two still good working detectors of panic, then we might get one of these solutions for 1.5 or so of this money. 1.5. That means we need something like, I would say something like 300,000 euros more to do to get any of this. If we take science, if we take engineering grade detectors, which I would not, I have fighted with the almost engineering grade detectors that ESO put into the wide field imager in the last 2 months of the project. I would not. One has to find the money, I think, for replacing the panic detectors, all panic detectors. The difference between the two solutions is that these detectors would be exactly the same pixel scale, so that nothing would change in a sense. So that what I presented as a observing strategy would still work. The 4K by 4K detector has 15 micron pixels. That means the area of a pixel is 18 divided by 15 square, that is 1.44. So the area of each pixel is smaller by a factor of 1.4, and also the entire area is, the entire covered sky is smaller by a factor of 4. The advantage would be that you have no gaps. You don't need this complex dithering pattern, which does not work reasonably without 5 positions. So you could maybe live with 3 positions, which would bring the exposure time or the necessary exposure time per pointing down, or the overhead time down. And also, if you have very good seeing, you gain the factor of 1.4 almost again for point sources, because the area covered underneath the star is also smaller. For seeing better than 0.9 arc seconds, you get basically the entire factor 1.4 back from less background. So it's not as bad as it is on the first side, but it's something one has to think about. I have decided that the 4K solution is also a possible solution only 2 days ago. I had to write a few lines of estimation. Okay, that's basically where I stand. The good thing, and I have to mention that also, the good thing about the 4K detector would be that the integration into a mosaic would not be needed. And this company that has done the integration, we had a bad, I think somebody was dying, has died or so. So it's also not easy to mosaic the 4 detectors if we go for this solution. On the other hand, since we were planning to mosaic the Mikado, that is the ELT first light instrument, to mosaic the Mikado detectors, but ESO took this task away from us. There are people in Heidelberg and our institute who are interested in integrating mosaicing detectors. So that's what I have what's next? That is my answer. And since 2 weeks ago, I'm exploring all the possibilities, but I cannot offer you solutions. Thank you.
Thank you very much. We have a few questions.
Your experience with the deterioration of the 2 detectors is very worrisome. Did Teledyne or anyone else offer a solution why did that happen?
Yeah, this is bad batch. And the problem was that I have mentioned on the in the Teledyne email that we have got these detectors in 2008. And these detectors were lying around in a cupboard for more than 3 years before we realized that there's a problem with this batch. The warranty was gone. Yeah, that's the thing. It's well known now. It's a bonding problem, and but we found out too late to get better things for nothing to back in.
Klaus, with the 4K solution, so the total cover field in the 2.2, for example, what will be the total cover field of the car?
You mean the field of view of this 4K detector?
View with the solution
26 arc 25 to 26 arc minutes. Spare. Yeah?
You said that the cost was basically the same to replace the 2K by 2K detectors and the 4K.
That's what I
understand that the 4K should be cheaper to fix it, and the 2K by 2K.
sorry. This would be if it's basically the same price, and that's what Peter was telling me after the phone call to Teledyne. It would basically be the price per pixel is the same.
Okay, that's not actually the information that I have from the detectors that we're working with. It might be that the detectors are different, but the 4K, as far as I know, is around $1 million.
Yeah.
With the electronics, well, the other was around 300,000 or a bit of 350.
Yeah, I was astonished as well.
I would certainly go for the 4K.
I was astonished as well, but I still think that Peter has done this. I was not with him, and I cannot tell you any details, but I have the impression that Teledyne, because Teledyne is the problem originally, they have, I think, some feeling that they should help us. That's all I can.
So maybe they're giving you better prices.
Yeah, exactly. That's what I mean.
Thank you very much again. The next speaker is Anna Pasquale, and she will talk about the survey of the verbal cluster.
So while we set up the presentation, I start. We switch science case now, and we talk about the galaxy environment and especially the environmental effects that are acting on galaxies in general. We are interested in galaxy environment because, as we know from the local group and the drone imaging spectroscopic survey, galaxies like to live together, either in galaxy pairs, in small groups, in richer groups, in clusters, all of which are aligned along the filaments of the cosmic web. Now, in all the 30 years that have been passed by since the early work of Alan Dresser, we have learned that galaxy evolution is not only driven by stellar mass, which is a proxy for secular internal evolution, but also by galaxy environment. Right. And the way we quantify right now galaxy environment is either by measuring the local density of galaxies or by estimating the dark matter mass of the halo that is encompassing, embedding a galaxy cluster or a galaxy group. All right? And we know that there is a galaxy hierarchy within this halo. We can split the galaxies between a central one that is the most massive, and all the rest of it are satellites. And as we know from observations and theoretical studies, central and satellites follow different evolutionary paths. So a central is the best role that you can have in a cluster or in a group, because there you interact with galaxy
Yeah, exactly. That helped in my case. Taking it out and putting it in again.
That allow you to accrete new galaxies and stars. So if you have new
Here it
galaxies,
doesn't.
you continue forming stars and accreting, assembling your stellar mass. Instead, if you are a satellite, you are unfortunately moving, orbiting within the potential well of your group, and therefore you are subject to tidal interactions, ground pressure, which all of which will make you lose your gas. Hot, diffuse, cold, whatever. And in time, a satellite will switch off. Star formation will be quenched. Okay? That's why the majority of galaxies in Virgo, for example, are red and dead because they have stopped their star formation activity and let their stellar population evolve passively. Okay, this is what I was telling you about. Thank you guys. Okay, so let me go to the right, yeah, right. So what are specifically these environmental effects acting on satellite galaxies? Well, they take different names in the literature. We, this morning, I think somebody mentioned strangulation or starvation. This is the slow removal of the hot gas, which is this reservoir for future star formation in a satellite. We have ground pressure stripping, which instead is the fast removal of the diffuse interstellar medium, being it an ionized or neutron, from a satellite. This is due to the fact that the satellite, as I said, orbiting is interacting with the intracluster medium, which strips the gas away. And the simulations show that the fraction of stripped gas increases with the intracluster medium density, as well the orbital velocity of the satellite and the halo mass of the host group or cluster. Then we have tidal stripping, which is mainly the removal of stars from a satellite due to its interaction with the potential well of the group or the cluster, or through the tidal interaction with the central galaxy. And finally, the harassment, which is loss of gas and stars due to fast and close encounters between satellites in that environment. The point to take home is that these effects are quenching satellites from inside in, outside in, right? They are removing the gas from the outskirts towards the center. So you may expect to find radial gradients in the stellar population of these satellites, because at different times gas is removed from different positions within the galaxy. Now, how these do these environmental effects I want to show you some predictions from simulations. These come from Betty, 2015, and they show the star formation rate as a function of time. And this for different types of satellites, different stellar mass, different orbits, also different environments, against Virgo. And depending on all these parameters, the run pressure stripping is able to quench the star formation activity, to reduce it, but also it can also leave it alone, so unaffect it, or sometimes even enhance it, because this is due to the shock when the satellites first meets with the intracluster medium, and the shock induce instability in the gas. For what concerns tidal stripping, these are the simulations of Chang et al. 2012. They assume a pair of galaxies, Milky Way-like and LMC, and they let them evolve over 7 gigayears. And then they plot the stellar mass density profile of the satellite with, as a function, galactocentric distance, for different kinds of morphologies of the satellite: a pure disk, and a bulge. And the simulations showed that this tidal stripping and the stellar mass loss is most efficient when 80 to 90% of the satellite dark matter halo is lost. Once the dark matter is gone, then the satellite starts to lose its own stars. And the amplitude depends mostly on the morphology. So you see that the changes are most dramatic for a disk satellite. In 7 gigayears, this satellite reduces its extent by a factor of 3, as well as the stellar mass density of a factor of 3. This has to happen, otherwise we wouldn't be able to, in a sense, justify the intracluster light that we see in Virgo. All right? Now, how do these environmental effects change the properties, the observed properties of these satellites? Well, have a look here, where I plotted the stellar age of satellites in black and centrals in gray as a function of stellar mass. So just look at the solid lines, right? So you see that below a stellar mass more or less of 10.5 in logarithm, satellites are always older than centrals. The stars in the satellites are on average older than those in the centrals. And this is a function of halo mass, you know. You take this relation and you compute it for satellites belonging to different environments with a halo mass that goes from 10 to the 12 to 10 to the 15 solar masses. And you see that the offset in age between the satellites and the centrals and between satellites themselves increases with increasing halo mass. So we learn that these environmental effects are best visible for low mass galaxies in massive environments, and possibly they are due to the fact that these satellites entered their environment early enough. They've been exposed for a long time to these environmental effects, run pressure stripping, tidal stripping, and have quenched their star formation earlier than satellites of the same stellar mass, say, living in less massive environments. I know that said like this is a little bit too quick, but stay with me. Then, in this plot here, you see the stellar metallicity of satellites and centrals as a function of stellar mass. And again, 10.5 satellites seems to be metal richer than centrals. And this is again a function of halo mass, right? Because something this offset in metallicity increases with increasing halo mass. What is happening? This result was pretty a surprise for us. And we explain it as due to tidal stripping, in the sense that these satellites here come from progenitors that were more massive than the actual present-day mass. So if the progenitor was more massive because of the stellar mass-metallicity relation, it was metal-richer. When it fell into the group, the progenitor was subjected to tidal stripping, lost part of its mass, even half of it, but kept the original metallicity encoded. And this is what we are actually measuring, right? So there is another trend that is very interesting, and this is the radial trend within a cluster. You can see here the fraction of quenched satellites, those that are not forming new stars. These are the yellow dots, as a function of cluster-centric distance normalized by the virial radius. And you see that as you move inside the group, the fraction of quenched galaxies increases. And this is, we think, due to the fact that here in the central region of a cluster, the intercluster medium is densest, and therefore the run pressure stripping is most efficient in removing the gas and quenching the galaxy. And you see it here as well. Here we have the fraction of galaxies without H-alpha emission, so say not forming stars, with H-alpha emissions, forming stars. And you see that this trend here is the same as here. Galaxies without emission in H-alpha, the number increases towards the center of the cluster, while we find preferentially galaxies with star formation activity in the outskirts of a galaxy. All right? Now, you may say, and you would be right in saying this, that these observational results are all averaged across a range of orbits, across a range of accretion histories, which we observer cannot measure directly. But we have a way to estimate these, that the accretion history and the orbits in a sense, in order to understand a better environment. And this way is offered us by, let me skip this because I don't have much time, by the phase space of clusters. So what am I plotting here? This is the peculiar velocity of satellites normalized by the velocity dispersion of the cluster as a function of cluster-centric distance, again normalized by the virial radius. And simulations have helped us in finding, identifying different regions. For example, this one, the satellites here within the virial radius result to be virialized in the simulations. So they belong to the cluster, will never leave it. All right? This part here are backsplash galaxies that have fallen inside the cluster not long ago, but they have eccentric orbits that they allow them to cross the cluster, get out the cluster, and swing back later on. And this instead is the population of galaxies that are unfolding now. Now take this region here, zoom it out, let's zoom in, and we see, these are the same parameters, we see that galaxies in the phase space are distributed along in a trumpet distribution that is better described by caustic profiles. So a caustic profile is delta V over sigma times R over R1. So the caustic profile that is in red is for a value of 0.1 and identifies all the satellites that are virialized. This caustic, the blue trumpet, instead, isolates these satellites here, according to simulations, that have recently accreted. So how recent is recently accreted? Well, you can use for example, cosmological simulation of the Lucia blazo and trace the last inform redshift as a function of caustic profile for different beings of stellar mass, different beings of halo mass. I'm not going into the details, they don't really matter here. And you see that those satellites that have a small value of the caustic profile fell in a redshift 1 to 2. Okay. And those instead that have a high value of the caustic profile, the blue thing, in the previous plot, fell in a redshift 0.3, 0.4. So, this gives you, in a sense, the average accretion history of satellites in different halos and of different stellar mass. And what we can do now is to attach to this accretion history what we observe. For example, the specific star formation rate that here we plot as a function of observed caustic profile. And you see, independently of stellar mass, well, at least for stellar mass is less than 10.5, you see the systematic trend of specific star formation increasing with increasing caustic profile, meaning that galaxies that are at the center, since they were accreted earlier, are all quenched. And star formation occurs only in the galaxies that have only recently or are infalling now. On the same, here you can see the stellar age that mirrors these trends. Those satellites that have a low caustic profile, no specific star formation rate, are the oldest, while satellites that have recently been accreted or infallen have a younger age, so they are less quenched. So I'm coming to the conclusion. So we have learned that the environmental effects are best visible on low mass galaxies, less than 10.5. They are best also visible in phase space, because there we can attach to the observed properties an accretion history, which we cannot measure directly, and also best visible in clusters, in massive environments. Do you remember I told you that environmental effects eat the galaxies outside in? So what we expect to see in these satellites is a radial gradient in the stellar population properties, whose amplitude will change, we expect, as a function of phase space, right? And accretion history. So what we propose to do is to select about 100 objects, 100 galaxies in Virgo, which sample the phase space of the cluster together with the filaments to which the cluster is attached to, through which now we have infalling galaxies, observe them with PMAS, and measure these radial gradients, their amplitude and their dependence on phase space, and therefore on the average accretion history of these satellites. Why the Virgo cluster? Well, can I have a minute to like that? All right, I can make it. The Virgo cluster is the closest. It is a cluster because we have X-ray emission. It has 10 to the 15 solar masses. It has a lot of galaxies that we can pick from. It is connected to filaments of infalling galaxies, as I told you. We have ample evidence of stripping, tidal and ramp pressure stripping. Look at here, the H-alpha wake of a galaxy in Virgo. And we have a wealth of ancillary data from the optical to mid-infrared that can help us understand the environmental effects. And what I want to add to this is that such a detailed study of environment in phase space has not been addressed by the present large surveys like LIFA, Atlas 2D, even Manga. Manga chooses groups, clusters, but doesn't check the phase space, which for us instead is extremely important because it goes back to the accretion history of satellites. And in this case, and for this reason, our suggested surveys is kind of unique. Thank you.
We have time maybe for one or two quick questions.
I won't acquaint the audience. Jorge.
For this interesting presentation, you will use themas in the feedback configuration?
Yes. Yes.
And may I have another question? the low mass galaxies, but start forming early, low mass.
Low mass in phase space, so from inside to inside, and especially and the filaments, because the filaments are the pre-accretion. So I would expect there to see something happening to the star formation activity.
Then thank you very much.
Thank you.
Next speaker, Alberto Manino, the Calar survey.
Hay que desconectar la luz. Si puedo acercarlo. No, tú manda.
Ahí tiene eso y ahí lo tenemos aquí. Un segundín, espérate un momentito, que no diga que hay señal. Vamos a hacerlo. Vamos a sacarlo. Rebelión.
¿Los Macintosh quieren?
Rebelión. Una cosa. Cierra un segundo el visor, tu proyecto. Bueno, sí. Vale,
Es más fácil hacer
perfecto,
esto.
perfecto. Muy bien, muy bien.
Suele
Mejor.
funcionar mejor, sí.
Sí. Sí. Porque es como ruido.
Pero no va.
Espera, ya está. Es
Ah,
que-
vale. Estaba un poco...
Ujú.
Ahora sí. Ok, venga.
Okay, let me start the timing. Okay, so this is a project that several people, including from IAA, this is a project that we are proposing to join two Spanish facilities with two state-of-the-art detectors. One is in the optical, one is in the near-infrared. The marriage of these two projects may lead to an ambitious data set which will have a great impact in all the astronomical areas from galaxy evolution to cosmology, and will be an order of magnitude deeper in terms of accuracy and volume than any spectroscopy redshift survey today. So in order to understand the possibilities of this project, I'd like to spend just a few minutes talking a little bit about the project, the host project, that should be combined with the Calar Alto facilities. So basically, I'd like to comment briefly about the cosmological framework of the project. So the universe seems to be darker than expected. So our current understanding of the universe says that the dynamical evolution of the universe is, at the present epoch, triggered by two competing effects. One is a repulsive, one is attracting effect, which is triggered by the dark matter. It's some kind of matter because it has gravity, it tends to cluster. It represents almost 24% of the content of the universe. And we have, on the other hand, this repulsive energy, dark energy, that we don't know neither what it's made of. But we know that it resembles like a perfect fluid with negative pressure, because the cooler and the larger the universe becomes, the stronger it's the effect. So in the last decades, there has been proposed and carried out several programs trying to carefully observe the universe, find evidence to constrain the different ingredients that build up our cosmological model, taking advantage that the different observables that we can measure with our instrumentation, they can be combined because they are independent, so they can be used to constrain our cosmological model. And one of those is in particular the one I want to refer, because it's correlated with the project I'm talking about, is the VAO, which is a proof to constrain the properties of the dark energy, in particular the equation of the state. So the VAO, it's been mentioned this morning, it stands for baryonic acoustic oscillation. It's nothing but an excess signal that we observe in the distribution of the typical distance between the galaxies, a particular length scale, a particular scale. So this bump, this signal, if we measure precisely the properties of the peak, we can understand the properties of the universe. Why is that? Because that peak, that excess signal, has to do with the properties of the universe when the radiation and the matter decouple after recombination. So the more precisely we estimate the peak, the better we understand the properties of the dark energy. And the idea is that the properties of the peaks has to do with the dark energy, especially with the equation of the state, and it's model dependent. So we can constrain the properties of this dark energy. Basically, there are two ingredients that we need to characterize the VAOs. One of those is we need a large sample of galaxies, a large number of galaxies. That's why we need great volumes. And the other is that we need exquisitely measured redshift. So we need a large number of galaxies and high precision redshifts. So in the last decades, most of the stage 3 projects estimating the VAO, they have all been spectroscopic surveys. That's why, because we need accurate photometric, we need precise redshift estimates for the galaxy, so to map out the structure of the universe. In this sense, JPAS comes to help. So JPAS proposes to use imaging to derive quasi-spectroscopy for galaxies. The idea is the following. JPAS is going to be the first stage for cosmological survey, in the sense that it's going to measure with such a precise, the VAO, so to be able to keep constraining the equation of state of the dark energy. So how JPAS is going to do it? How is JPAS going to provide such a high accurate redshift estimates using photometry? And this is the trick. The trick is the following. If you combine a photometric approach, in the sense that we all know that CCD has more sensitivity detecting faint sources, so we can go deeper, we can observe more galaxies, so we can increase the survey volume in the universe. If we design and build, as we did, a fully dedicated telescope with a wide field of view, in the sense that we can observe many galaxies per shoot, if we design and build a big, homogeneous and efficient imager, so we can have many galaxies per shot. And if you design and manufacture one of the state-of-the-art filter system in cosmology, which is the one I will present to you, it's a 56 narrowband, 150 angstrom width filter system, you can derive precise photo-C, as precise as almost the spectroscopy redshifts. What is the trick? The trick is the following. People working on photo-Cs, we know that there is a strong relation between the number of filters you use to map out the spectral distribution of a galaxy, and the precision in the redshift estimate. And that precision, you can see different surveys in the past, like Sloan, Combo 17, even a number survey which was done in this house. And at the very top, at the very end of the plot, you have the JPAS. So if you have as many as 56 narrowband filters, you can get 0.3% photo-C redshift estimation. Just for you to have an idea, this is like 10 times more accurate than Sloan photometric redshift, and this is 20 times more accurate than DAS photo-C estimation. So this is an example of the filter system that we have manufactured. I like for you to take this message home, is that with this filter system we have quasi-spectroscopy, in the sense that we have a resolution power of 60. So as you can see in this example, you can resolve most of the spectral features of the galaxies, absorption and emission line. So you not only can derive the redshift for the galaxies, but you can also derive physical properties of the galaxy. So after fulfilling all these requirements, the big CCD, the large field of view, a fully dedicated telescope, the filter system, after fulfilling all these requirements, JPass is going to produce these state-of-the-art photoseeds, which are 0.3% estimates for 90 million galaxies in the universe, combining luminous red galaxies and elliptical emission line galaxies, plus millions of quasars up to redshift 5. JPass is 50 times larger than any current spectroscopic survey, 50 times. Due to the enormous volume it's going to cover, the cosmic variance is negligible. So if you think of a statistical analysis like luminosity or mass function, the final results that will come out from JPass, they are definitive, up to redshift 1. Although by construction, by definition, JPass is a cosmological survey in the sense that the main goal is to estimate the radial VAO with a stage 4 precision. It's actually, by construction, 4 different cosmological surveys. It's the VAO cosmological survey, it's the galaxy cluster cosmological survey, in the sense that we will be able to estimate a huge number of galaxy clusters in the universe, so we can estimate the delta M in the cosmological model. We will have a supernovae cosmological survey, because we are repeating the observation many times to cover all the filters. And finally, given the pixel scale and the quality of the site, we can do lensing. So it means that we will have a lensing cosmological survey. But apart from that, due to the multi-band nature of the survey, basically we can do any single astronomical project. So we have people working from minor bodies in the solar system all the way to large-scale structure, or even working on alternative theory to gravity. I like to call it, JPass is like an astro market. So you go and you pick the information you need for your science case. As I said before, given the repetition in the exposures to reach the final depth in all the filters, we will be able to estimate, to identify and characterize variable objects, galactic and extragalactics with an unprecedented precision. JPass, by construction, taking into account that it's like a photospectrum with a resolution of 60. The large field of view, the huge size of the camera, is one of the largest cameras in the market. We will be able to do IFU-like science for millions of spatially resolved nearby galaxies. It's like a pixel-by-pixel multi-wavelength analysis. And there is another feature of JPass that I really like it, but most people don't realize, is that this is a really multiple survey in the sense that, well, let me show you. This is an example of the kind of IFU-like science that can be done. This is just a small fraction of what is going to be the JPass field of view. And if you zoom in, it's so big, the image, that it takes some time to. So this is the kind of information that we will have. We will have pixel by pixel multi-wavelength information for 8,000 square degrees of the sky. But what I want to say is that this is a particular feature of JPass, is that since we are using so many narrowband filters, what we can do is recombine the filters and sacrifice a little bit the photoseed precision at the expenses of going deeper in our observation. So we can go from the original set of 60 filters, we can recombine and go to a 20 filter system, increasing the depth, sacrificing a little bit the depth, and we can also go to the long filter system, the 5 filters, so we can go deeper and deeper and deeper at the expenses of changing the photoseed resolution. And this is very powerful, because depending on your scientific case, you can go deeper or shallower, and you will be using exactly the same observations. You don't need to re-observe changing the filter system. All the filter systems are already included in our filter system. So JPass is a Spanish-Brazilian collaboration. It's the IAA. It makes an essential part of the collaboration. Chicho Benite is the PI of the project. He works here at the institute. We have the FEFCA. It's a foundation created to carry out the JPass. In Teruel, also the Brazilians folks are involved from Rio de Janeiro and Sao Paulo. Obviously, we are 100 members in the collaboration. They are involved many tens of institutions and several countries in this collaboration. Just for you to know, for people not from Spain, Teruel is in this position here. It's in between Madrid and Barcelona. Approximately, there is a dark spot in Europe. It's actually the darkest spot inside Europe. This is the site. This is TEFCA. This is the headquarters in Teruel. This is just a publicity of the place. This is the good news for JPAS is that all the instrumentation is already prepared. We have the observatory built. We have 3 telescopes working in the same direction. We have the main telescope. It's a 2.5 meters telescope, which is going to run JPAS. But we also have several auxiliary telescopes to take care of the photometric calibration of JPAS. So this is like 3 telescopes working at the same time to guarantee the exquisite calibration that we need to derive these extremely accurate photos for a huge millions of galaxies in the universe. So this is the secret. The JP cam is a redshift machine because the combination of these multi-Narrowband filters with this 14 science CCD with the pixel scale makes possible to cover 8,000 square degrees in a few years. And why is that? Because if you think about the classical way people do photometric redshift surveys, it's like you have several filters and you have to repeat the observation many times. But because of the design of the camera and the smart combination of the filters, we end up with a survey speed, which means that we can cover 1 square degree of the sky with all these 56 filters in an hour. So it makes possible to carry out the survey, these 8,000 square degrees, in a few years, in 7 or 8 years, depending on the condition. And it's important to say that this smart design, this camera, which is one of the state-of-the-art cameras in cosmological survey, it's similar to a 5,000 multiplex spectrographs, but it's far cheaper. It's like an order of magnitude cheaper. So basically, few more details. JPAS is going to survey 8,000 square degrees, combining north and south hemisphere. The typical depth is going to be for the detection image, which is going to be R-band, is 24. But the narrowband is going to be a bit shallower, going from 21.5 to 22.5. And that is going to give us, roughly speaking, we will be able to detect luminous red galaxies up to redshift 1, emission line galaxies up to redshift 1.4, Lyman alpha and quasars up to redshift 5. We will survey a cosmic volume of 14 gigaparsecs, so that's why the cosmic variance is going to be negligible. We will not take care of it anymore. So this means that we will observe with the basic survey 400 million galaxies detected with this multi-band information, from which 90 million of them we will have this almost spectroscopic information. 90 million galaxies with almost spectroscopic redshift information. So this is 50 times larger than any current spectroscopic survey at the time. So that's why JPAS is so powerful. So this is just an example of the expected redshift distribution for JPAS. It's going to peak around 0.5 in redshift, and as I said, complete down to a magnitude 22 in the narrowband. So this is the proposal. This is the suggestion for Calar Alto. We propose to carry out in Calar Alto using PANIC a combination of the optical data from JPAS with deep near-infrared in the J and in the KS. Going as deep as J and KS in magnitude 21.7 and 21.4 respectively, covering 200 square degrees, we can produce 7 million galaxies with 1% precision. This is the Alhambra Gold Catalog 1 precision. Again, this is 3 times as accurate as Sloan data, photometric data. But we can also provide 3 million galaxies with this almost spectroscopic precision. 3 million galaxies, just combining the data. And 70,000 quasars, identification and characterization of 70,000 quasars. This number comes from this J and KS magnitude scan, represents 80% of the galaxies. This is the magnitude that you need to go to observing the near infrared. 80% of the galaxies detected in magnitude detected in the I band down to magnitude 22.5. So due to the large area that we plan to cover, this 200 square degrees, cosmic variance will be already negligible. This data set will surpass current state-of-the-art data sets by more than 1 order of magnitude in terms of mass sensitivity and volume. It's an order of magnitude deeper in all sense. So the synergies between both facilities, Calar Alto PANIC and Alhambra Observatory and the GPCAM, will lead to a legacy data set with a large impact in the Spanish astronomical community in basically all areas. So why including near infrared? There are a long list of reasons to include the near infrared to the optical. One of those is that even if we don't include the near-infrared in the JPass data, we will already have these high-quality photosys. Anyway, we are producing that. But if we include the near-infrared data, we can increase the amount of galaxies with this high-quality photosys estimation. Why is that? Because as we go to higher redshift, most of the spectral features enter in the near-infrared. So just including this J and K as information, we can increase this high-quality photosys sample. Obviously, we can enhance the stellar mass estimate of the galaxies if we include the near-infrared, especially for those with a large dust and extinction. As you can imagine, this 200 square degrees combination of the JPass and the panic will be useful for either galaxy evolution and cosmological analysis for this reason, especially to understand how different galaxy types evolve or assemble their mass at different environments, as it's been explained in the previous talk, and also understanding the structured growth history of the universe due to the fact that baryonic matters, considering including a bias factor, and traces the underlying dark matter distribution. Something that I think it's, these are the numbers that we had computed. So we think that to cover 200 square degrees to that depth in those two bands, we need like 200 clear nights from Calar Alto. This is the estimate, we can talk later. This is the expected mass distribution. So here in this plot, I'm representing the stellar mass of galaxies as a function of the redshift. Purple represents the Alhambra survey, which is a well-known survey from this house. And the different color represents the different magnitude cuts of that sample. So the idea is the following. If we impose a cut in magnitude in the I band at magnitude 22.5, this is the in red, this is the expected stellar mass distribution for JPass in this combination. So we expect that this sample will be complete almost down to a stellar mass 10 to the 10 solar masses. So this is, again, an order of magnitude deeper than current spectroscopic surveys. Finally, I'd like to emphasize that JPass the people working in JPass, the people making JPass real, has long experience working with near-infrared data. We already have the Alhambra survey, which was a great experience carried out in Calar Alto, but we also have the experience working from space-based data with near-infrared from the cluster lensing and supernovae with Hubble. Both projects almost manufactured at this very house. JPass has already started in many senses, that we already have the telescope, we already have the filters, we already have the camera. Today it's being delivered to the observatory. We have already started to run the small telescope. This is the 80 centimeter telescope, which is devoted for the calibration of JPass, but since it has a very particular filter system optimized for the identification of stellar features in order to identify the stars, to calibrate JPass, we have already started this smaller survey, which is going to cover the same area as JPass. And it means that we have everything prepared for the databases, for the pipeline, for the people, everything is ready. And has already started with a different survey. So it means that as soon as we open the dome and JPass start taking images, we will be able to reduce the data and get scientific results. And this is something important to be taken into account, because I think that guarantees that a synergy with the panic in Calar Alto will be successful, in the sense that we have everything prepared to process, to reduce, to calibrate, and to deliver the data to our colleagues. And I think that's it. I don't know, maybe I went too fast, but if you have any questions, I will be happy to try to address them. Thank you.
Yes, we have time for a few questions.
I can keep speaking, if you don't.
I suppose that you were assuming that Panic had the form.
Yeah, for sure, absolutely. So there are not bad news in the website. So that's kind of
After the Klaus talk, what would you be your preference? Having 4 2K 2K or 1 4K 4K?
One. Because the differing pattern takes a lot of time. So for us, for a survey purpose, one single CCD is much more efficient if the CCD works well.
But remember that the field of view will be smaller.
I know, but we need to, just fill in the gaps. I need to do the numbers. But probably filling the gaps is going to take more time than reducing a little bit the field of view. Certainly.
One more question?
plan to extract the photometry? Sort of, it will be complicated. You have like 30 pictures, and you want to add KN.
It's trivial. No, I'm joking. No, it's a complicated part that we have already a lot of experience because we have been working on several projects similar to JPass. One of those is the Alhambra survey, which was carried out here in Calar Alto using 23 filters. The class was using 16 from HST. We have JPass is using 12. Now it's using more, but the technique, the idea is the same. So we've been working on that problem for many years. So I think it's one of the smallest problems we have in the survey.
It was part of the thesis of David Cristobal.
Exactly, and my thesis as well.
You too,
My thesis. So my thesis was devoted to the photometric redshift estimation of the Alhambra survey. So that's why I say that we have everything prepared. All the experience, all the knowledge, all the tools, they has been simply transported and scaled to JPass. That's why I'm so confident that we are well prepared and we will do a good job.
Well, thank you very much.
You're welcome.
The next speaker, Catherine Turon, is inside the computer. Inside my Skype. Hopefully it can work.
Inside the computer, we hope so. We hope so.
Ah, vale.
Que soy de... Sí, de hacer una vueltecita.
Eso sí, lo vamos a alimentar.
Ya he puesto el micro también.
Hello.
Hi, Catherine. Can you hear me?
Yes, very well. And you?
Yes, everybody can hear you. So when you want, we can start.
Okay, so I can start. Okay. Okay, so I will speak you about the ESA Gaia mission and its possible synergies with Calar. So I will, in fact, mostly speak about Gaia, so present the points of Gaia in operation and see the problems and solutions. Go through the first catalog, which has been now published from a month about, and say some words about the further data release to see what we can expect in 1, 2, 3 years, etc. And finally, look at the possible synergies with Calar. So I will just recall about Gaia that it is really a unique experiment by several aspects. So it has been launched in December 2013 and went through 6 months of commissioning. So this unique characteristic is first the accuracy, the astrometric accuracy, which is clearly unrivaled and which varies, of course, as a function of the target magnitudinal colors. It is a systematic sky survey from 3 down to 20, about even more, 20, nearly 21 magnitude, which is a very big interval of magnitudes. So it will be more than, it is more than a billion objects observed all over the sky, and simultaneous astrophysical characterization by spectrophotometry for all observed objects, plus radial velocity and spectral characteristic for the brightest part of the program. So on the average, about 70 observations per object will be done over 5 years, and maybe more years if the mission is extended. So we don't know yet. So all objects right in this magnitude limits will be observed. What stars or solar system objects or quasars or galaxies. So the routine scientific observation started in July 2014 by 1 month of ecliptic pole scannings, which means that all the scans were going through the 2 ecliptic poles, and especially the south ecliptic pole that area was covering a big part of the Large Magellanic Cloud. And after that, it went back to the whole sky scanning law, the nominal scanning law. So until July 2016, we have collected 440 billion of astrometric measurements, more than 100 million of billion of photometric measurements, and already 9 billion spectra. So proper astronomical numbers indeed. So the limiting magnitudes in operation, so not the spec now, are astrometry. For astrometry and photometry is between 3 and 20.7 in the G band, so the Gaia band. And in fact, it will be managed to also obtain astrometric parameters for stars brighter than 3 using the Gaia sky mappers. And the spectra will be obtained down to 16.2. So the in-orbit commissioning, many things were nominal, as the attitude and orbit control, the micro-propulsion system, the phase array antenna to get all the data back to the ground, the onboard clock, which is very accurate and very accurately synchronized, and all the CCDs and associated electronics and data storage. So all that is functioning perfectly. But there were a number of unexpected issues which were at first very worrying and finally have been tackled progressively. So first, it was constated that there was a high transmission loss, which was understood to be due by contamination of water ice. And so there were successive decontamination, first during commissioning, and then 3 others, the last one in August. So each time some mirrors, or all mirrors depending, were heated so that the water ice evaporates. And indeed, the transmission of the mirror was recovered. So other attitude perturbations were the impacts of micrometeoroids. And you have an example of that in the upper figure. And so you see the impact of a micrometeoroid on the solar panel and back to normal with the attitude control on board. So there are also micro clunks, which apparently comes from the solar illumination of the solar panel. So another thing which was very worrying at the beginning is the periodic basic angle variation, which are much larger than expected. And this is, of course, serious as this is the key to the measurements of the parallax and avoiding systematic errors. And in fact, very careful calibration limits possible systematic effect to micro-arc-second level. So this is completely tolerable. So finally, there has bad discovery of a strong stray light, clearly modulated with the spacecraft rotation, but it was 2 orders of magnitude, 2 orders of magnitude larger than expected. And in fact, it is scattered light from the sun and from the very bright star and the Milky Way. And you see on the second image, the reason for that is that there were some fibers just at the edge of the solar panel, which were outside the panel and on which the light, especially of the sun, are diffusing. So the problem was to see how to handle that, and in fact it is mainly for spectroscopy that it is a problem, which means that the limiting magnitude of the spectroscopic observation have been lowered, and that a special windowing strategy have been adopted. So the whole sky scanning law means that the integration time per CCD is 4 seconds, 0.4, and the crossing time of the total focal plane is about 45 seconds. So between 2 fields of view, there is about 100 minutes, and after that all patterns are repeated every 6 hours. And after 5 years of observation, there will be 40 to 240 epochs with an average of 60, 72. So you see on the left the resulting scanning of the sky at the end of 5 years. It is in equatorial coordinates, and so in blue you see the trace of the pattern of the ecliptic plane where there are less observations, and on high ecliptic latitudes you have many more patterns, many more observations. And on the right you have the observations you will have for any source. So you see that the number of observations and the separation between observation is very special. But however, there are many observations, so it will be strange sampling for variable stars, but anyway, quite nice sampling, in fact. So next slide shows the content of the very first Gaia catalog, Gaia data release number 1, which have been published on the 14th of September. And it uses, in fact, a 12-month of data spread over 14 months of mission. And they use about 23 billion of transits across the galaxy. And it has to be noticed a number of simplifications. So first of all sources have been treated as single stars. So you have in the figure, you have the Tegas, so the one part of the Gaia data release number 1, one part for which you have parallaxes and proper motion, and these are the number of observations per source. And so you see that indeed it is quite unequal for the moment. So the next slide shows the result for the data release, what we call secondary sources, because only positions are variable for these sources. So there is 1.1 billion sources all over the sky, with small between quotes, between already 2 million stars in what we call Tegas, Tycho, Gaia, Astromet. Je ne sais plus quoi, sorry. 2 million parallaxes and proper motions. And there is also a part with light curves of Cepheids and Lyrae, 3000. Position of magnitude and magnitudes of 2000 ECRF quasars to connect the Gaia catalog to the external quasars. And of course, a lot of documentation, interrogation tools, visualization and cross-match tools. So I really invite you to go to this website where the archive of Gaia is available. And you will see this, there is a bookmark which is visualization. And if you go there and activate the zoom, you will see a lot of details there. So the next slides show one of the details. And once you activate the zoom, you go further and further in the spatial resolution. So you notice a number of details, and the galactic plane, of course, in black. And you also see very clearly the pattern of the sky mapping by Gaia. So you clearly see that some areas are less observed than others. Those which are with less bright areas of the sky. So the next slides show you the position of the data release number 1. So on the left, you have the initial Gaia source list, which was the source, the list of stars from which the data reduction started. And on the right, all the new sources detected by Gaia, which are already 500 million new sources. So the limiting magnitude, as I said already, is 20.7. The alignment with the inertial reference frame is better than 0.1 mass, with a rotation better than 0.03 mass per year. And typical position uncertainty of Gaia DRM position is about 10 mass. And the comparison with the position of the radio position of the quasar observed for the initial reference frame are better than 0.3 mass, which is quite good, with no systematic difference with radio position of more than a few tenths of a mass. So next slide shows the subset of the data release for which there are parallaxes and proper motion, which have been obtained by using initial positions, the Arcos and Tycho 2 position, because with only 14 months of data, you cannot disentangle between parallaxes and proper motion. And if you're ready, you can go to the next slide. You can see there that with Gaia measurements, which are the red dots, you can have various proper motions. And if you add, if you take into account the Tycho 2 position, which date back 23 years, of course, you can fix the direction of the proper motion. So if you can come back to the previous slide, you see that taking as prior Hipparcos and Tycho 2 positions allowed to compute parallaxes and proper motion for the 2 million sources present in Tycho 2, which are all mostly brighter than 11. It has to be parallaxes and proper motion are totally independent of Hipparcos parallaxes and proper motions, as well as Tycho 2 proper motions, because only the position have been taken into account. So the Tegas parallaxes have a median parallax uncertainty of 0.3 mass, and the systematics at the level of 0.3 mass also. And the error levels reflect exactly the early scan coverage and the geometry of the scan. So if you can go 2 slides further, please. So here is a comparison between Tegas parallaxes and Hipparcos parallaxes. And you see clearly that already the Tegas parallaxes, even with this only 14 months of Gaia data, are already 3 times more size than Hipparcos, with about 20 more sources. And the line in red at the bottom shows what we are expecting after 5 years of mission. So the next slides give a first glance of the result with a share diagram as an illustration. So if you look at the 2 HR diagram on the left, you see on the left the Hipparcos absolute magnitude and colors. Gaia parallaxes, and you see that the main sequence and the red clump giants are much well defined, and you only see the elongation due to the extension, which is not corrected here, of course. So in all these cases, it's only stars with parallax uncertainty better than 20% and some stringent precision on the magnitude and the color. And on the right, you have the 41,000 stars, which are closer than 100 parsec, coded by tangential velocity, where the high velocity stars are coded in pink, and you see clearly that they are below the main sequence, and the young stars are coded in blue, and you clearly see them at the top of the HR diagram. So next slide, please. There you have the photometric precision, so for the whole billion sources. And the error, the graph shows the weight and mean G magnitudes for stars with about 100 transits. So the calibration of systematics is presently at the level of about 3 millimagnitude, and you see that the precision is about 1 millimagnitude. And the strange pattern for the brightest stars is just due to the way these stars are observed, with gates to limit the observation time, because they are too bright to be observed for the crossing of the whole focal plane.
Catherine, 2 minutes.
How many? I did not hear. 2 minutes?
Yes, 2 minutes.
Okay, so I will rush a little more. So here you have two examples of the light curves, which are also published for a large number of Cepheids and RLI in the Large Harmonic Cloud. So you notice the accuracy of the curve, even for the 18.5 RLI array. So next slides are warning about this catalog, which is of course a very preliminary catalog. And there are holes in the scanning of the sky, as you can see on the right on the image there, because no stars with less observed 5 than observation or unsatisfactory astrometric parameters have been included. So there are some incompleteness in very dense areas and missing components in closed systems. So in Tegas, there are about 20% of the Tycho II stars which are missing, even though they are in the secondary sources, and especially many bright or very red or very blue or high proper motion stars are missing. So systematic errors on parallax are indeed sensible, and they are about the level of the random the random error. And there are still correlation between position, parallax, and proper motion. So it has really to be noted that you do not have a big improvement, as usual, in square root of n when you average the parallaxes of stars in small areas, such as clusters or Magellanic Clouds. So rather huge individual values. So next, in the next release, which is in about 1 year, you will get much more. Indeed, only parallaxes and proper motion with Gaia-only data, and the photometry not only in J but also in BP, so in blue and in red, and also 3 to 5 million radial velocities for stars brighter than 12. The spec there was radial velocity better than 1 kilometer per second, and currently it's even better than 0.5 kilometer per second. So in the further data release, there will be about 100 million mean radial velocity expected, plus atmospheric parameters, chemistry, and interstellar reading obtained directly from Gaia data, and also orbital solution, also for exoplanets, for large exoplanets, object classification, and orbits for solar system objects. So an example in the next slide about spectra. And so you see the spectra are quite well defined, and you will get in 2 years already, in 2.5 years, we had already collected 10 billion RVS spectra. So the next slide shows the schedule. It's in French, but it's self-explanatory. So there will be other intermediate release nearly every year before the final catalog, which is expected to be in 2022, 2023. So finally, the possible Gaia-Cara synergy. So what would be, of course, very interesting is to get a very detailed spectroscopy for Gaia stars with the most precise astrometry. So having a very high resolution spectroscopy. And also for all the part of the Gaia program for which you don't have a spectra, so stars fainter than 16, 17, to have a radial velocity and abundances for these fainter stars. And also to have a determination of the absorption extension towards a huge number of stars with known distances given by Gaia. So for binaries, but especially for exoplanets, Gaia will give an unbiased magnitude-limited exoplanet census of all types of stars, and we are expecting up to 20,000–30,000 astrometrically detected giant planets to about 500 parsecs. And the best periods are better, smaller than 6 years. And so, of course, from the ground, radial velocity follow-up and detailed chemistry of host stars will be very welcome. So I wanted also to notice that there is a special website for photometric alerts detected by Gaia, and that ground-based follow-up are, of course, welcome. So I invite you to go to see that. And also there is another website, observatory website from Institut de Mécanique Céleste for the improvement of orbits of solar system objects detected by Gaia. So there again, there is a big collaboration of ground-based observatory to follow this object and improve the orbits. Okay, so that's all. Thank you very much, and sorry for not being with you.
One question? No questions? No questions. Thank you.
No questions. Thank you, Catherine.
Okay. So thank you.
Thank you.
Bye.
So the next speaker, Benito Moralejo, will talk about commissioning the post-down MRS spectrograph, and you will have 95 seconds for...
Well, hello to everyone. I will try to be briefly because probably most of you are starving. Then I would like to present myself a little bit since probably I'm a new face for most of you. My name is Benito Moralejo and I'm working in the Astrophysics Institute in Potsdam, Germany, in the InnoSpec group that this is led by Martin Roth and also Stefano Minardi. And I come here to present you what is the Potsdam MRS spectrograph. That this is included for people who attended this morning at the talk of Martin Roth in the proposal number 1 that he did in the morning. Well, first of all, say that the Potsdam MRS spectrograph is a multiplex spectrograph. That this is an updated, that this is a derivative of the Muse spectrograph, which has been shown that this is a very successful instrument, right? First of all, also say what is the meaning of the MRS initials. MRS means multiplex Raman spectrograph, because this is the immediate purpose of the instrument, right? For those of you that are not familiar with Raman spectroscopy, I will say briefly, that Raman spectroscopy involves sending what is a surface, in this case, this is a piece of skin with a monochromatic light, and recording what is the scattered light. Because the Raman effect, there will be some shift in energy of the scattered light, and with this one we can get a fingerprint of different materials that can be used in science or medical applications. This is because this spectrograph is being used in the project that is multiplex Raman spectroscopy aus der Astrophysik für die Medizin. For giving a small example about what is a Raman spectroscopy about, I will show you here what this is a camera picture that was taken with a microscope, a camera picture that was integrated in a microscope objective, showing two different materials. One is PS and PMMA. PMMA is polymetal metacrilat and PS is polysterol. When we illuminate and when we record the Raman spectra of these two materials, this is the Raman spectra that we get. I mean, resolution is not so good, but well, let's say that this is a specific fingerprint for each of these materials, and there are two peaks that are specific for one of these materials. The peak in 600, we can construct a build map with the height of this peak, and we can distinguish what it is, what should be the material that is PMMA, And if we create a map that this is center or this is focused in the peak in 1035, we can distinguish other materials, like this is the PS, right? For us, for people who are working with random spectroscopy, the improvement is clear. This, as for you astronomers, that we can perform faster Raman studies. And this has been shown that this is very interesting for different areas, like, for example, in medicine, that we are talking about, right? But because of the features or characteristics of this spectrograph is equally useful for integral spectroscopy and multi-object spectroscopy in astronomy. Giving a brief overview about the instrument, first of all, this is a fully refractive fiber-fed optical system manufactured by Wilney System. Wilney System is a French company who already manufactured the 24th spectrograph that is being used now at the moment for the Muse spectrograph that is in Chile. Now the wavelength coverage has been shifted to the blue part. For the Muse spectrograph is between 465 nanometers to 930 nanometers. Now we are covering between 350 and 900 nanometers, but also we are improving the transmission at blue part of the spectrum. The BPSG, because the update is that I showed before, had to be completely redesigned, and now is working instead of at 30 degrees, now it's working at 8 degrees with an angle of incidence of 425 lines per millimeter. Here it is shown what this is the first of the diffraction of the BPSG that we are using, with a peak of almost an 80% at around 550 nanometers. And this is the shape, how the BPSG that we are using looks like. The input side of slit length is 118 millimeters, that if I remember well, I think that this is 20 millimeters larger than from Primas, and this is plus minus 59 millimeters, considering 0 as the optical axis of the instrument. As a detector, we are using a 4K by 4K E2B detector that with great index anti-diffraction protein, that probably most of you know about it. The instrument was designed for working with an input depth number of 4.33 and with a magnification of 0.52. And linear dispersion was calculated to be around 0.13 nanometers per pixel with a modest resolution of about 1200 and 3000 for the blue and red part of the spectrum respectively, using a 50 micrometers fiber. Here it's shown what is the optical design of the spectrograph. This is the CMAX optical design. This is the part of the collimator, the part of the camera. At the part of the collimator, there is a first lens, that this is a plain concave lens in which all the fibers will be attached in immersion, hopefully. Two single lenses, and here there is a triplet lens, which in the middle we have a calcium fluoride lens. The reason is to improve the performance at blue wavelengths. This is the BPSG working at 8 degrees. Just after the BPSG, we have a doublet with another calcium fluoride lens, two single lens, and finally this is an spherical lens that will become also the window at the D-word, and will create what is the vacuum for the part of the camera. Once we have this optical design, all of them was integrated in this extractor, in which I would like to highlight 3 different parts. First of all, this is a shutter, that this is heritage from Primas. This is a cylinder with a rotation, and at the end of the cylinder, there is also the possibility to install different filters to avoid second-order diffraction. The part of the camera, the D-word, was completely designed by the AIP, and now instead of using a closed-loop nitrogen system, is using a cryogenic system, which avoid to use, we don't need to use nitrogen to get 115 degrees, I think, or 100, for cooling the system. And finally, there is a focusing tool that formerly for the Muse was in this part, but now was installed in this part. This is a micrometer screw. When this is moving the fiber slit unit together with the first length of the spectrograph. This is this is acting like a focusing tool that later I will show you some results of that.
I didn't understand, the cooling system is?
It's cryogenic.
Cryo-Tiger.
Cryo-Tiger, sorry, Cryo-Tiger. Well, once the old system was assembled, we performed what is the optical performance of the instrument, and it was done with mainly two different parameters. First of all was image quality. The requirements were the image quality and a square energy of 80% enclosed in a 30 by 30 micrometers square area. That is 2 by 2 pixels of the E2B detector, and in terms of magnification, to be sure that the signal of all the fibers are images on the detector. Right? This was not a requirement, but the affectant test was also carried out at different temperatures, between 15 degrees, 20 degrees, and 25 degrees, to know how the system, what is the behavior of the system with this at this temperature. Well, for all of you who are very interested or more interested in know how the acceptance test was done, I would suggest to take a look in this publication that you can find in AstroPH in archive. Yeah, I will show briefly what were the results of that. Yeah, in terms of magnification was calculated for 5 different wavelengths, creating 2 different objects at the input inside the input field of view. Yeah, and finally was the parameter of magnification was also calculated. Right. All magnification for all wavelengths are below 0.52, but not only at 20 degrees, but also at 15 degrees and at 25 degrees. We can see that this is also fulfilling the specifications. In terms of image quality, what we can see here, maybe the quality is not so good, but anyway, we can see what is the PSF for this spectrograph. Created the PSF of 5 different wavelengths, started at 900 nanometers up to 405 nanometers for 5 different objects inside the field of view. This is the center and this is the borders. With software, what's calculated, what is the square energy inside of these spots. The square that this is here is 30 by 30 micrometers, and you make an idea about what is that. And this is at 405 nanometers. And you can see like all energy is above 80% at 20 degrees. Not only at 20 degrees, the test was also performed at 15 degrees and 25 degrees, and we can see that all values are above 80% of energy. Well, this is a picture of the instrument. What I would like to show here is the instrument is real. It's at the AAP. We can use it for Raman instrument. We can use it. Unfortunately, still the camera has been installed, but the CCD chip is not the final one. The final one, I think that we have problems with the bonding of the CCD chip, and I think today we received an email that now is the new cameras at the AAP, probably will be installed in next days, in probably 1 week, 2 weeks. Then all the results that I'm showing now are performed with a CCD, that this is an engineering grade CCD. It's not the final one. Once we receive the spectrograph, we proceed with the installation of the fibers, the testing of the fibers at the input. There are 420 watt input fibers with 114 micrometers core, of which 400 fibers belongs to a 20 by 20 matrix fiber bundle, like you can see here, and there are another 21 fibers that will be used, that individual fibers that will be used for another specific applications like testing frequency cones or illumination of the, for custom application, let's say. Okay. Other important part is the data reduction. For those of you who already work with PMAS, probably know the P3D software. Now, last version of P3D software has a new entry that it is here, that is MS1. Yeah? And I must say that still is not 100% compatible, but this is around 90% compatible. This is some things we need to add to the keyword, as keywords in the fits files, but it will work very soon. Well, once the camera was attached, we proceeded with the focusing. A total of 9 focus series was carried out, was performed moving the micrometer screw, which is moving the first lens of the collimator, and using a spectra of mercury and neon spectra, mercury and neon lamps. Yeah? We choose 9 different spots. 3 spots are 914 nanometers, 3 are 615, and 3 are 404, for 3 different objects. 1 at the center, the optic galaxies, and 2 at the borders. The result is what you can see here. This is the position of the focus tool. And this is how the PSF looks like when you are moving the focusing tool. What we are seeing here is the sum of the AAT parameter. That this is that's here. Yeah? This is the length of one side of a square, which contains 80% of the total flux of the spot. And what we can see here is that for the sum of all AAT parameters for the same wavelength for three different objects has this shape. Ideally, we expect to have a best focus when this parameter is minimum. We did the same with the focus with the different spots at 650, more or less at the middle of the CCD, and the same with the wavelength at 404. You can see, like, unfortunately, the focus is not at the same focus position, but this is something that we expected, right? To get a trade-off, a good trade-off of that, we assume all the spots, we assume all the AAT parameters, and this is what we have. Yeah? Hopefully, we get a very good trade-off between all the spots. And the focus position will be, this is about in a position of millimeters, 2.5 micrometers, right? At the focus position, this is how it looks like. This is a square, 60 by 60 micrometers. This is 4 by 4 pixels because the magnification and the size of the fiber core. And this is the parameters, this is the full width at maximum in the dispersion axis, that all are below 4 pixels, but this is here, these values are much better than at the bottom part, at the top part, sorry, which are very close to 4 pixels, but in the spatial axis, I would show that this is all values are below 3.5 pixels, which shows that the image quality is quite fine. Now this is how an halogen spectrum looks like. We took 20 fibers, just more or less at the middle of the CCD, and you have here what is the normalized spectra. Here you can see what is the fiber-to-fiber throughput, which is quite fine. Yeah, this is more or less all very close to 1. And if we make a zoom of these two pixels, we can see the different parameters of this adjustment. Yeah, that this is showing that the distance between two maximums is around 10 pixels. Full width at maximum is 3.3 pixels. And finally, Martin pointed out in the morning that we have 3 different spectrographs. First of all, we have a MISO spectrograph, which was not designed for using with fibers, but the AAP did a very good work, and now we are testing with fibers at the input, under of 400 fibers, and it is working fine. We have now this spectrograph, that this is the MRS spectrograph with this BPG efficiency, and we have another one, right? Still is not commissioning, we are waiting to manufacture all the pieces, but this is an exact copy of the Potsdam MRS spectrograph that this is here. The only change is the efficiency of the BPG. If the first one was improved for the blue wavelength with a maximum of about 80% at 550 nanometers, the second one, this is improved more for the near infrared, with an efficiency of more than 60% starting at 500 nanometers. Well, the conclusions, I would say that the Potsdam MRS spectrograph has been presented to the astronomy community. Its immediate purpose is in Raman spectroscopy, but the system is real and can be already found in the AIP facilities. The acceptance and the commissioning of the instrument has shown a superb and an excellent image quality. And finally, this is perfectly useful for IFS and MOS in astronomy. Thank you very much.
Thank you very much for keeping in time. We have time for a few questions.
There's a very quick few questions. The first one is, you said that you were approved between 15 to 25 degrees, but by design, is the design a thermal or is it not?
No, this was not in the requirements.
So you will have to go to 5 degrees, let's say. Do you think you will have issues or?
Yeah, I mean, we can check it, but we will check it because in Berlin it's very cold. I can open the windows and I can tell you.
The other thing is, so is the coating the one that gives you the separation between the fibers on the solder sheet? Is the coating of the fibers? So you don't give any cap or have a big growth design in the center lead or something like that?
Yeah, this is the center lead is designed with big growth.
Ah, okay.
That's the yeah. It's here you have.
It's an extra room. Okay.
Yeah, the point is the arrangement of the fibers. You can see here. This is 421 fibers, and starting with a double fiber that this is here. There is a group of 20 fibers, and the 22nd fiber is another. Is another, but it can be changed.
It's so why when you said that you have to find a trade-off between the blue and the red, one position of the bigger and the other. So is the tilt of the detector going to help somehow when you put the final one?
Well, inside the data sheet of the E2B, say that the flatness of the CCD is plus minus 10 micrometers. Inside of our requirements for wind light was that the focal plane will be inside plus minus 10 micrometers. In the worst case, you can be 40 micrometers far from the ideal position. Well, hopefully, what we have here is that are not very far. This is kind of trade-off, but I mean, I must say that probably you realize that I say that the spectrum was designed for between 350 and 900 nanometers, and now we are seeing up to 914. Yeah? This is the reason is because for some specific measurements in Raman spectroscopy we need to see up to 915 nanometers. How we can do it? The reason is with CMAX simulations we realize that this can be done moving this slit 2 millimeters above. This 2 millimeters above is changing here. What we are seeing instead of 900, you see 915, and here you see 365. I mean, we are not perfectly now working on the nominal characteristics, or we'd say nominal features of the spectrograph. Probably when I change this and I go back to just at the middle, probably the foot width and maximum of the part of the red will be much better, and probably the curves will change. But we will do it when this is the new CCD installed. The new CCD is installed probably in a few weeks.
So thank you very much again, and thanks to all the speakers. Any announcement except
just for people going to the data session, if we go from here 7:30